Black holes are the most iconic things in our universe. Their mind-bending properties were debated for generations, and were pondered by some of the greatest minds of our time. Today, we know that black holes are real, and as a result, we can begin asking the next big questions. What lies beyond them? How did they die? Most of all, what is the biggest black hole in the universe? Well, it's likely that TON-618 is up there with the biggest, if not the biggest in the universe. And while we don't know much about it, its profile is truly magnificent. This radio-loud and hyperluminous quasar was once thought to be just another star. But we now know that this monster's photonic relay is emanating and calling us from much further across space, over 10 billion light-years into the void. But is this beacon of the cosmos really what we think it is, with so many properties that push the limits of our understanding of black holes? TON-618 may have another explanation. But until we find that, we must assume that this record-breaking beast is the largest and most massive black hole in the entire known universe. TON-618 is the catalog title of a quasar located at the center of a galaxy approximately 10.37 billion light-years from the Earth, in the constellation of Canes Venatici near the galactic North Pole. Despite this unfathomable distance, it shines with an absolutely visual magnitude of -30.7. This number equates to the brightness of over 140 trillion suns, making it one of the brightest objects in the known universe. We will cover more about why this is in a moment, but in a quasar, the mass of the black hole usually indirectly corresponds to the amount of light it produces, and as such, numerous calculations have estimated the mass of this engine black hole to be over 66 billion times the mass of our home star. This mass is both hard to visualize and hard to fully appreciate, but for some sort of perspective, the Milky Way's central black hole is approximately 4.3 million times more massive than the Sun. Sagittarius A is largely responsible for anchoring our entire galaxy together, which could be up to 200,000 light-years in diameter, yet its mass doesn't equal 1,000th of the total mass of TON-618. Thanks to our study of black holes, we can use what we already know about its mass to estimate its actual size, and the results will truly blow your mind. If our calculations are correct, then the radius of its event horizon, the boundary beyond which nothing can escape, including light, which gives it the distinctive black color, will be approximately 194 billion kilometers. This radius dwarfs even our entire solar system, and then some. The solar system's diameter is a little under 300 billion kilometers, whereas TON-618's event horizon diameter is close to 400 billion kilometers. But then, how is this black hole so massive if the emissions we see are from billions of years ago, when the universe was significantly younger? The universe is about 13.8 billion years old, and this likely formed between 1 and 2 billion years after the Big Bang, meaning it could have been as young as a billion years or less when the light reaching us now began its intergalactic journey. This is very young for a black hole, and yet the signals are indicating that a black hole this young is larger than anything we've been able to find in the universe billions of years on. After all this time, there's no telling how big it has become, but there are a few ideas on how it might have come to be so large at such a young age. The main theory is that this black hole was a direct collapse black hole. Instead of being formed by a dying star's supernova, this black hole was formed by a supermassive gas cloud collapsing under its own gravity. This process can also take all the stars within the gas cloud with it, rapidly consuming thousands more distinct sources of mass. This process would generate an inconceivably large supermassive black hole, and is the expected way in which most engine black holes at the center of galaxies formed. In the future, we may re-estimate the black hole's measurements and come up with new figures. But for now, these are the facts. But what about its history? How was this black hole discovered? And when did we realize that it was the most massive we had ever found? TON-618 was first noted in a survey of faint blue and white dwarf stars around the Milky Way's galactic plane in 1957. Back then, it was mistaken for another blue star, and was listed as the 618th member of the TON-618 catalog of globular star cluster, thus coining its name. However, moving in the 1960s, astronomers started noticing radio-loud sources of light which appeared similar to stars. But the source of this radio energy was unknown, and thus the term quasi-stellar, meaning star-like, was contracted to quasar, and astronomers continued to investigate them. It was Martin Schmidt who then noted that the Doppler shift lines in the quasar spectrums were not consistent with the expected redshift of stars, and so these sources of light must be emanating from much further away. Gradually, higher resolution images and X-ray photographs indicated that these radio-loud sources were emitting were from the centers of distant galaxies. And the light reaching us from these quasars is billions of years old. But how does a black hole, scientifically the darkest thing in the universe, even shine in the first place? Let alone shine brighter than stars a millionth of a percent of the distance away. Well, the process begins with the immense gravity of central galactic black holes. When gas and matter orbit the black hole, they orbit the area at immense speeds, as do the light and energy released when they consume things. When a black hole destroys something, it does through the trivially named process of spaghettification. As you get closer to the singularity, or center, of the black hole, the gravity becomes so exponential in its increase that even a difference of a few million kilometers can lead to vastly different levels of pull on the object, essentially shredding up whatever it is. The gases from this shredded matter form a disk around the event horizon of the black hole and can orbit it, forming an accretion disk. When this disk orbits, it swells at unimaginably fast speeds, and the friction generated releases unbelievable amounts of heat. The accretion disk can also cause black holes to emit plumes of plasma, known as relativistic jets. These jets travel away from the black hole at nearly the speed of light. And this and the accretion disk shine so brightly together that the light we can observe drowns out the surrounding galaxy. When it does this, we call these illuminated black holes active galactic nuclei. A sufficiently luminous active galactic nucleus is classified as a quasar. With our growing understanding of quasars, the hunt was on for more, and before long, a radio survey in Bologna in 1970 detected strong radio emissions from this so-called star, and thus it was reclassified as a quasar. Marie Helena Ulrich then collected the spectral data from the object. She detected the spectral emission lines, the lines in the spectrum that occur from the emission of light from an object. From an analysis of the redshift of the spectra, Ulrich determined that TON-618 must be very far away, and hence it ranked among some of the most luminous quasars ever detected. Furthermore, the emission lines detected on the spectrum were very wide, including in the broad line region of the quasar, a spectrum of light from an orbital area beyond the accretion disk. These are indicative that to the light emanating gases around the black hole must be traveling incredibly quickly, calculated be a terrifying 7,000 kilometers every single second. This told scientists that the black hole creating the quasar must be exerting an intensely strong gravitational influence. The size of the broad line region can be reverse engineered from the brightness of the quasar, and given the size of the region and its orbital speed, this black hole had to be one of the largest ever discovered. The mass was estimated at its official figure of 66 billion times the mass of our Sun, and using black hole equations, the event horizon radius was determined from this to be over 1300 astronomical units, thus giving it a new classification, an ultra-massive black hole. But in spite of all these mind-blowing statistics, it's important to remember that we cannot see TON-618's surrounding galaxy, and therefore, we know very little about it. While the math suggests these massive figures for the black hole, some have argued that we may be mistaken. There are questions over its true nature, and if its sheer size so early on in its life wasn't enough to cast doubt, the nature of quasars does too. Quasars are a phenomenon more typical of the early universe, hence their massive distances from the Earth. They are more commonly found between 9 and 10 billion light-years away, because the universe was teeming with them at that age. While we do see some nearer to us, the number is nowhere near as high. This is because in the billions of years since these quasars occurred, the engine black holes of the universe have had time to consume much more matter, increasing their event horizons. Once a supermassive black hole exceeds a certain size, they are large enough to completely swallow matter up rather than shredding it. Less shredded material orbits within the accretion disk, and the light generated no longer outshines its host galaxy. So, there's a contradiction. Is there not? If smaller black holes have more favorable conditions for quasars to occur, why is one occurring around the largest black hole in the universe? Unfortunately, we currently don't even have a way of knowing. Perhaps the galaxy surrounding TON-618 was immature at the time, and there was enough matter orbiting it to be shredded up despite the size. Or perhaps its gravitation influence is just too great so that the swirling gases are orbiting too fast not to shine. But this isn't the only argument against TON-618 as a quasar, either. Some point to the theoretical size limit of black holes, predicted by some to be 50 billion solar masses. Any larger, and they suggest black holes would start to lose their accretion disks, and would not be able to maintain their size and constant intake of matter. Anything larger wouldn't shine at all. And of course, the fact that this black hole was so massive so early on cast doubt. Even if it is explainable by direct collapse black holes, why don't we observe other black holes of this size from that area of the universe? Why does TON-618 stand out as such an anomaly? Well, although it does display all the expected properties of a quasar, the true explanation behind it could not yet be known. Most quasars happen to look like stars in the Milky Way, so who's to say that quasars don't also look like some sort of other undiscovered phenomenon in the early universe? Who's even to say that we understand quasars and black holes? Perhaps it's not our estimations that are inconsistent, but our knowledge of the phenomena themselves. After all, we propose the theoretical size limit for structures in the universe based on a uniform distribution of matter at the Big Bang to be about 2 billion light-years, and yet we have observed quasar groups, superclusters, and gamma-ray burst rings which vastly exceed this size. Perhaps the problem lies in the limit of our imagination, and the true size and mass benchmarks of these phenomena are much, much higher than we expected. It's impossible to cast a clear judgment as we're missing some quite major pieces of observational evidence. If something similar was discovered, we may be able to compare two abnormal quasars and gain a better understanding. But quasars are the brightest things in the universe. It's unlikely that there's another one of this magnitude just hiding out there that we have yet to discover. So for the time being, we just don't know. TON-618 may be the largest black hole in the known universe, but what are the other giants it is vying for the privilege with? Well, the previous record holder was the obscurely named S50014+81. This was another quasar which was reverse-engineered, and the measurements suggest a black hole of around 40 billion solar masses. However, some believe this figure may be exaggerated. When a relativistic jet fires in the direction of the Earth, its quasar appears even brighter, so much so that it has own type of name, known as a blazar. This black hole's jet happens to be pointing in the direction of Earth, and so some suggest its unusual brightness is not actually indicative of more mass. But whatever the case, it's still an enormous black hole. Another enormous black hole lies about 1 billion light-years from us, and it is the monster at the center of the largest known galaxy. IC1101 is a supergiant elliptical galaxy over 6 million light-years in diameter, and it is estimated to contain over 100 trillion stars. We cannot see inside the galaxy due to its luminosity, and it is too far away to be directly measured. But IC1101's black hole has often been considered the biggest by default, because galaxy size is typically representative of black hole size. But due to the variables, the estimation comes in quite broad, between 40 billion and 100 billion solar masses. This is likely another one we'll never be able to properly assess and measure, but once again we know what lies inside is probably larger than our entire solar system. And then finally, there's HD 1821 plus 643. This black hole is also a quasar that lies much closer to us, and was considered the most massive in 2014. Unlike the others, its mass has been precisely measured to be around 30 billion solar masses. This gives it an event horizon radius of 1150 astronomical units, approximately 14 times the distance of Pluto from the Sun. Black holes are scary enough on a stellar scale, but they can grow to sizes so great it becomes hard to imagine how something cannot lie beyond the boundary of its singularity. We can speculate on the size and mass of TON-618 all day long, but don't forget that this was its size 10.5 billion years ago. Largest black hole or not, its size now must be truly incredible. Or is it? Perhaps it has reached the size limit for black holes, and what happens to a black hole when it cannot consume and begins to break down is anybody's best guess. With all these questions, it's depressing to think that they will probably always remain just that, questions. But who knows what discoveries are waiting for us in the future? The observable universe is growing, and eventually its radius is expected to expand beyond 60 billion light-years. With that extra distance, who knows what else could be waiting for us in the shadows of the early universe? And if you thought that was big, the area beyond the observable universe could be millions of times bigger. While TON-618 may be the largest black hole in the known universe, just take a minute to consider what else might be lurking out there, trillions of light-years into the void.